Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the previous lecture, we were discussing about the diastereoisomerism in cyclic systems. So, we were discussing about the derivatives of cyclobutane, and we have seen the case with 1,2 and 1,3 disubstituted cyclobutanes in the last lecture. So, now we will continue our lecture in this direction and we will see what happens when you have 3 substitutions in cyclobutane. So, that is 1, 2, 3 tri-substituted cyclobutanes. So, there are also a few types possible. Type 1, when all the substitutions are same. So, let us try to draw those molecules which are the possible isomers of 1, 2, 3 tri-substituted cyclobutane. I am just taking one example with methyl. Sorry, this is 1. This is the second one. And this is the third one that is possible to have for this type of molecule, where you have 3 equivalent or similar substitutions. So, what we see in 1, we have a sigma plane. That sigma plane contains the unsubstituted carbon atom, this plane which is here. So, therefore, this molecule is having a symmetry C S. So, C S point group, and therefore, it is again a meso compound and optically inactive. If we look at the third compound, this third compound also has the same sigma plane, therefore, belongs to C S point group like 1. So, it is also optically inactive. Like 1, so it is optically inactive. But when we look at the compound number 2, this compound 2 does not have any symmetry. Therefore, this belongs to C1 point group, and hence it is optically active and exists as a pair of enantiomers. Right? Let us see the next type, which is type 2. When 2 substitutions are same and third one is different. When 2 substituents are same, but third one is different. So here what we have are these isomers. So if we look at these isomers carefully from 1 to 3, these 3 isomers do not have any symmetry. So they belong to point group C1. Therefore, they exist as pairs of enantiomers, and they are optically active. When you look at the other two, 4 and 5, both of them contain sigma plane. I hope you are able to identify the sigma plane very easily, and the sigma plane is this one. Therefore, they as usual belong to point group CS, and hence they are optically inactive. So this is how one can try to draw different isomers of substituted cyclobutanes and find out how many isomers are possible and which ones are optically active and which are optically inactive. So these isomers 1, 2, 3, 4 and 5 are diastereomers of one particular compound. The third type of these compounds are where all the 3 groups are different. So let us draw those isomers of the compound where all the 3 substituents are different. What you can see in all these 4 diastereomers is that they have no symmetry and hence they belong to point group C1. So, all 4 of them would exist as pairs of enantiomers and are optically active. So, now we can extend this to tetrasubstituted cyclobutane derivatives, and in that the known example is trioxylic acid. Let us see the possible different isomers of trioxylic acid, which is tetrasubstituted cyclobutane derivative. So, let us quickly draw the isomers that are possible for trioxylic acid. So, if you look at these 5 isomers very carefully, of course, they are all diastereomers. Why? Because they are not mirror images of one another. Therefore, they should be termed as diastereomers. But then what we see is that all these 5 diastereomers have some or the other symmetry that is present in the molecule. What symmetry do we see in these molecules? We see in case of 1, 2, 3 and 5 the sigma plane, which I am drawing like this. sorry, this 5 has again a sigma plane. So, 1, 2, 3 and 5 they have sigma plane, but the molecule 3 has inversion center I. Therefore, all the molecules are one or the other way symmetric. Therefore, they are optically inactive. So, even if this particular molecule has 4 chiral centers, but they are all optically inactive because the molecules contain either a sigma plane or an inversion center. So, this is how we can draw several isomers of tetrasubstituted cyclobutane. A real example is trioxylic acid. So, let us move to the next part of the course, where we will discuss about the isomerism in cyclohexane derivatives. So, again as usual we were discussing while discussing about while discussing about butane, the cyclobutane derivatives, we have taken 1, 2, 1, 3 and so on. So, in case of cyclohexane also, let us start by considering the 1, 2 disubstituted cyclohexanes. So, if we draw the cyclohexane in planar form, the cis isomers can be drawn like that, or like this, and the trans isomer will be drawn like this. One methyl group upwards or one substitution upwards, one substitution downwards. So, now here there are two possibilities. Suppose the two substituents are same. So, if we draw these two substituents as same in the chair form which we have learnt earlier, then this x is up and here the axial bond is upwards, and it is this is axial and this is equatorial. So, the axial bond is up and the equatorial bond here is up. So, both are up, and if you do this flipping of the ring, what we get is the following. So, this becomes axial and that becomes equatorial. If this is carbon 1 and 2, here the carbon 1 and 2. So, here AE and EA, that is axial equatorial and equatorial axial, are energetically equivalent, therefore they cannot be resolved at room temperature. Although they belong to the point group C1, they are chiral compounds, but since the flipping energy barrier is achievable at room temperature, so both the isomers, both the conformations are possible at room temperature, therefore they are non-resolvable enantiomers. And hence therefore they exist as racemic mixture, as a racemic mixture. So, let us try to draw the mirror images of these molecules. And then if we try to do a flipping of this molecule, we would see this one. That is the flipped structure of dimethyl 1,2-dimethyl cyclohexane, and then if you rotate the molecule by 120 degree about the central axis, this central axis, what we would get is this one. So, therefore, what we see is the structures 2 and 4 are identical, and therefore, 1 and 4, which are mirror images, you have flipped the structure 1 and made structure 3 and simply rotated the molecule by 120 degree, you have arrived at the structure 4, which is identical to 2, and therefore, 1 and 3 are enantiomers, and they are not resolvable enantiomers because this flipping that occurs at room temperature spontaneously. What happens when the two substituents are different? Suppose X equal to chlorine and X prime is equal to bromine. So, let us draw the molecule in its chair form. And the corresponding mirror image. Now, just like before, if we flip this 1, what we would get is the following. Structure number 3. Now, if you rotate the structure 3 by this axis about 120 degree, what we would get is this new structure. So, what we see is that these 2 and 4 are not identical, 2 and 4 are not identical, and what we see is that 1 and 2 are enantiomers, 3 is not mirror image of 1. Therefore, 1 and 3 are diastereomers, and what we see are that 3 and 4 are homomers, right. So, in this lecture we have seen 2 different variations of cis 1,2 disubstituted cyclohexane derivatives and their possible isomers. So, we will continue from here in the next lecture.